Right, so there we are recording. This program is about the laws of nature, and what it shows you is how unsatisfactory the present scientific picture of nature actually is. And as we go through the program, hopefully what we're going to do is sort that unsatisfactory part out for you. So here we go.
Hello. Since ancient times, philosophers and physicists have tried to discover simple underlying principles that control the universe. In the 6th century BC, Thales declared everything is water. Aristotle believed all of creation was forged from 4 elements: earth, air, fire and water. Newton more successfully laid down the law of universal gravitation, and as we speak, contemporary scientists are struggling to complete the task of string theory, the quest to find a single overarching equation that underpins all physics and can perhaps explain the organisation of everything in existence. But are the laws of physics really facts of life? Is what is true in physics true in all areas of existence? Is it even true in other areas of physics?
So that's the first point, when he's asking the question, are the laws of physics true in other areas? So that means things like biology. Now, the study of biology and the study of physics are both the study of the same matter. That's a true or false question.
It's true.
It's absolutely true. So if you're studying the same matter, it's reasonable to assume that there's a common set of rules of governance for biology and physics. So that's what we want.
With me is Mark Buchanan, author of a new book called Ubiquity, which claims to identify universal principles that could underlie everything from an avalanche to a world war to a crash in the stock exchange to a forest fire. We're also joined by the physicist Professor Frank Close, author of Lucifer's Legacy, The Meaning of Asymmetry, and by Nancy Cartwright, Professor of Philosophy at the LSE, and author of The Dappled World, a study of the boundaries of science. Frank Close, some people claim that Aristotle held back science with his insistence on the 4 elements, earth, air, fire and water, and this search for simplicity was rather damaging. Would you agree with that?
Well, I don't know if it was damaging. It's certainly the case that intrigues me that for 3,000 years, science has progressed very successfully on the belief that there is some unity behind it all that we're trying to elucidate out of the complexity that we see around us. And although it's progressed that way successfully, and I personally think that is the way forward, I've begun to ask myself a question quite often as to whether there really is a unity out there that we're walking towards, or whether we're trying to impose a unity for psychological reasons on something which is actually very complex.
When Newton was searching for his laws, was he searching for a sort of truths of nature or truths of the laws of physics, do you think?
Certainly Newton made a great advance in bringing together things that at first sight you would never think were related at all. I mean, to be able to realise that a falling apple is controlled by the same law of gravity, as we now call it, to the way that the moon goes round the earth and the earth round the sun, was a tremendous insight. I often wonder if the earth had actually been covered by cloud, so that we'd never known of the stars and the moon, whether Newton would have been able to do what he did, whether science would have developed in a different way and order, and if ever we meet aliens from another planet, it'd be nice to know if their science developed the same way as ours. But Newton certainly was a great figure in the development of science. I think it is perhaps simplistic, but perhaps also arguably true, that if you want to say where did modern science begin, it was with Newton.
Mark Buchanan, how would you define a law of physics?
Well, I think a law of physics generally is some pattern that is first observed somewhere in nature, whether at the subatomic level or at the level of, say, ordinary materials, liquids and gases, that is so simple that it seems to cry out for some explanation. There are all kinds of patterns. There are extremely complex patterns that don't look much like meaningful patterns at all. And if you see a pattern like that, you generally don't try to make inferences about laws underlying those patterns. However, if you notice that you put a gas into a box and measure the pressure and volume and temperature, and always find that those 3 numbers fall on some extremely simple and orderly curve that follows a very simple equation, you can be pretty sure that there's some underlying order to that system. And so I think what a law is, in my mind, is really an extremely simple and elegant way of describing some kind of order that we have recognized in nature, and also that we have come to understand a little bit about where that order comes from in terms of deeper principles.
If a law such as Newton's first law of motion, everybody perseveres in a state of rest, works in one area of physics, is it sensible to assume that it would work in another area?
Oh, yes and no. I think, for instance, we know that Newton's laws apply to the motion of galaxies and stars and planets, and there's overwhelming evidence that that's true. We wouldn't just blindly take Newton's law and try to apply it to the behavior of, say, pressures and volumes of a gas.
That's right. Newton's laws were worked out in a mathematical way through observation and with abstract thinking, and they're about physics. He called them laws of nature, and they really do seem to work in the real world. What does that tell you?
Well,
laws of gravity put men on the moon, that sort of thing.
It tells me that we could have a lot of confidence because we've had 200 years of using them or more. We can have a lot of confidence that when we run into systems which are very similar to the kinds that we've been studying, that Newton's laws will continue to give very good, very precise, very accurate descriptions of new cases. So it was one of the things that Mark mentioned. It was a great breakthrough of Newton's in contrast to the previous Aristotelian physics. It was a plank in Newton's platform to say that heavenly bodies and earthly bodies were the same and would obey the same kind of laws of nature. Previous to that, it was thought that there was terrestrial mechanics and celestial mechanics, and that there were different kinds of bodies that behaved in different ways. And Newton said, no, wherever you've got masses, they're going to behave in the same way, whether they're the masses of the planets or the masses of cannonballs, or, as it turns out later, the masses of molecules. So I think the success of Newton's laws over a very, very long period of detailed predictions that work out provide us with very good reason to think that when we encounter systems which are like those systems that we've been looking at before and which are in the kinds of environments in which we've looked at them before, we can expect to use Newton's laws to make very accurate predictions. It doesn't tell us, I think, what we should expect when we encounter different kinds of systems.
Just a second, Frank. Do you think that fundamental rules can be found and applied right across physics, Nancy Cartwright?
I think we do not have sufficient evidence to put a lot of money in that program.
That's a very important thing to say. I don't think we have sufficient evidence to put a lot of money in that program. So what she's saying is that science isn't going to come up with an answer where we have laws which explain everything. But, and this is a very important but, the old way of thinking is that science would make everything predictable, like classical physics. So what we're looking for, wrongly, is laws which make prediction. What nobody's noticed and what nobody speaks about in this program is that we found another set of laws, different from classical physics, called the laws of chaos. And we know by a mathematical proof which Poincaré wrote, it is impossible to write any law of prediction. But that's only because you want one. Nature also needs adaptable laws to develop into biology. So what human beings are trying to do is to make something fit a previous misconception about reality. Instead of looking at what you've got, the laws of classical physics, single outcomes, the laws of chaos, infinite number of possible outcomes, which allow you to explain something like a snowflake, which has an infinite number of possible different details, all unpredictable. So you've already got exactly what you need, but you just can't see it.
Right.
So once again, same old human problem. So let's get back to the program.
And we do have, we've had, Frank said that there were this history of looking for unity and finding it, and that science had been driven for 3,000 years that way. But it is important to remember that the history of science is the history of both successes and failures, and that lots and lots of hunt for unity have failed, and a few have succeeded, and that as well as learning about some things that are unified, we've learned that at different periods that some things are disunified.
Let's stick to the laws of physics for the
Yes.
moment, because let's try to sort that out. in the limited time available. You're saying, it seems to me, that the laws of physics, as discovered even by Newton, cannot be applied right across physics, that they refer to a special, limited area of experience, knowledge, and so on.
Yes, what I'm saying is that our evidence for them is that they apply in these limited experiences.
On the law of gravity, for example, you say that it has limitations because we're talking about closed systems. I've read your book, so could you just tell the listeners what you mean by that and why you think the law of gravity has limitations and what those are?
Yes. Let me give a very controversial and striking example. Contrast dropping cannonballs off the Leaning Tower of Pisa with an experiment that drops instead paper tissues off the Leaning Tower of Pisa. Now, the first case, when you drop the motion of the cannonball is affected by the pull of the earth. In the second case, the motion of the tissue, let us imagine, is affected by the pull of the earth and the push of the wind. Now, in the first case, we have the law of motion, F equals ma. And
force equals mass
times acceleration.
Yeah.
The basic law of motion, very familiar from GCSE science. And can we apply this law to study the cannonball? Yes, we can, because even though when I described the cannonball, I said its motion was affected by the pull of the earth, and the pull of the earth isn't something that's any of those words I said. It's not force, it's not mass, it's not acceleration. We know, because Newton taught us, how to think of the pull of the earth in terms of these more abstract concepts of physics. Newton taught us the law of gravity. So that the
we
pull
know
of
about
the
gravitational pull. Now,
right,
what's the contrast with
well,
the paper
contrast
handkerchief?
with the wind is that with the paper tissue is that we'd like to use the law of motion, force equals mass times acceleration. We know it's subject to the pull of the earth, so we know that the pull of the earth exerts the force of gravity. But what about the push of the wind? Push of the wind isn't something that we have a law that tells us what it does. So in order to bring the tissue, the behavior of the tissue, into and under the laws of physics, we have to figure out some way to be able to represent the push of the wind as a proper force in physics. And you're not allowed to do it just in an ad hoc way. We actually have, in the case of the pull of gravity, we have a formula. And so the question is whether or not the push of the wind can be brought into the domain of physics.
That's a really bad example to use because the push of the wind doesn't mean anything to most people. The atmosphere is subject to turbulence and chaos, which is another set of rules on top of physics which are not predictable. But she didn't say that.
No.
So let's choose a much better example. Instead of a cannonball and a tissue paper, let's choose two examples which we can make sense of. One is the motion of three equal-sized bodies in space, and two, the motion of a chaotic pendulum. So if I take a chaotic pendulum, or two bodies in space, they are completely predictable physics. A harmonic pendulum ticks backwards and forwards completely predictably. Two bodies in space move around a common center of gravity completely predictably. Gravity makes absolute sense. But if I introduce one more body to the system, if it's of equal size, the predictable motion of the bodies has gone completely. You need to state that. It's gone. So have the laws of physics been switched off? Certainly not. But you've added another set of laws on top of the physics, which means that all predictability has been lost. Now that is the three-body problem, and Poincaré has written a proof. There are no solutions to the three-body problem. There are an infinite number of possible outcomes. Two bodies, a single possible outcome. So unless you've got chaos separated from classical physics, acting on top of classical physics, you can't explain something as simple as a chaotic pendulum. Remember, a single pendulum, simple harmonic motion, you put one hinge into it, it becomes chaotic, the same as the three-body problem. And the physics seems to have been switched off. It hasn't. The physics is still working, but now you've got a feedback loop and an extra bit of extra part of the system which is not conserving information. So the whole system becomes unpredictable, and nobody mentions that. So you can't make sense of the program.
Right.
It seems to me what you're saying is that these laws work within closed systems. If you've got a closed system, deep inside a thermos, inside a battery, or you've got a clear, almost controlled experiment like cannonballs from Pisa, known as in gravitational pull, bang, then you're okay. If you've got systems outside that, then the laws of nature are almost contradict sometimes or interfere with the laws of physics. Frank Close, what's your view on that?
I don't think it's that they interfere. What it is that the law of gravity is very simple to apply when you've just got two bodies, like the sun and the earth. The moment you get a third body in there, the moon, for example, you've got the sun on the earth on the moon, the sun on the moon. Already at that level of 3, it gets almost impossible to solve. And so you have to start making approximations. The moment you're dealing with the wind, it's getting extremely difficult. That's why the weather forecasting is so difficult. The basic underlying laws at the level of atoms and molecules and gravity and so forth, we know. We can work them out and apply them to individual bits and pieces. But when you look at large systems where you've got lots of these things competing together, it becomes at the very least a problem for a computer to solve, and even then it becomes very impractical.
Mark Buchanan, in your book Ubiquity, it seems to me the book starts with these 3 scientists in the end of the 80s sprinkling grains of sand one at a time onto a tabletop. They did it through a computer because it would take a lot of time and dexterity to do it manually. And then what happened?
What they discovered, to just get it out in the open, is a generic pattern of dynamics and change that occurs in the sand pile, but that also turns out to, well, mathematical signatures of it show up in many other settings. Now, one of the interesting things is if you did this experiment with droplets of water, say on the top of a lake, you'd get very boring results because you'd drop a drop in. The ripples would go away, and the lake would be a tiny, tiny bit higher, and that you could do that all day, and you'd never find anything very interesting. What's interesting about a pile of grains is that it's an irreversible situation. So you drop the grains, the pile builds up. Each grain, when you drop it, it falls, it gets locked in place and affects the silhouette of the top of the pile. And when future grains get dropped on top, they always get dropped on top of the setting that's already occurred. So every grain gets locked in place and affects the whole future out of which this pile grows. So it's a very simple non-equilibrium or irreversible process. And so the reason physicists are interested in it is it's so simple that one has the chance to hope to try to come to some deeper understanding of it. So anyways, what these 3 physicists found is that as the pile grows, it ultimately reaches a steady state where as many grains on average fall off the edge of the table as you drop in from the top. And it comes to be poised in a state of extreme unpredictability and instability, which is called the critical state. How this instability manifests itself is that when you drop the very next grain, you can not only not predict the details of what's going to happen, where the avalanche is going to be and how it's going to progress, and where all the different grains are going to end up in the end, but you cannot even predict the rough magnitude of what's going to happen. So the grain may just fall and stick and trigger nothing at all, or it may trigger an avalanche involving 10 or 100 or 1,000 or 1,000,000 grains. And there's a particular mathematical rule known as a power law, which indicates that there's no sense in the idea of there being an average size or typical characteristic size for the avalanche that occurs. There's really a kind of democracy of scale at work in this problem. So the system treats avalanches of all sizes as being effectively equivalent.
I know this is...
So what he's talking about in a democracy of scale, let's put that into better language. What he means is actually Zipf's law, that there is an inversely proportional ratio between the scale and the frequency of events. And those events are completely unpredictable. So he's talking about mathematical rules which are unpredictable. Now, it's only because human beings have tried to suggest that everything in the universe was going to be predictable that we're still trying. That's just tradition. The reason that nobody can make any sense of chaos is it is just matter, systems of matter behaving directly to mathematical laws. Western eyes don't see that. What they see is everything must be behaving to the laws of physics, which then must explain everything else. The laws of physics have been misinterpreted, and they are not seen as matter and space behaving to mathematical rules. So if you're trying to find a single kind of physics and unify everything, you aren't going to do it, because you've got classical physics, quantum physics, and chaotic physics. You've got three different kinds of rules which provide you with everything you need to explain nature, but you can't see it. So that's the problem. It's the fact that you can't see there's layers and layers and layers of more complex mathematical rules on top of the simple mathematical rules we call classical physics, and you can't access them and unify them under the umbrella of the laws of mathematics, because you're looking for a single kind of physics and you can't find it, because there are three fundamental kinds of physical laws: classical physics, single outcomes; quantum physics, probable outcomes; chaotic physics, infinite outcomes. Exactly what you need to explain things like genetics, which have probable outcomes; snowflakes, human faces, an infinite number of possible outcomes; and two bodies in space, a single outcome. So you've already got everything you need to explain nature, but you can't see it. Basic human problem again.
I don't think this is simplifying what you're doing, but I want to just move to what I think is the centre of it and then bring the other two in. What we're talking about is a critical state. The critical state is where something happens to this sand. The critical state you also see in crashes of stock markets, huge forest fires where there haven't been huge forest fires, and so world wars. The First World War is a wonderful example of that. Man takes the wrong turning, student kills two people, bang, away we go for 4 years, and then maybe for the next 6 years, and so on and so forth. Now, one thing that worries me, that I caught in the book, you talk of the special organisation of the critical state, but yet you also say that the result of running these avalanches of sand through computer after computer to find a pattern was the result that there was no result. So I can't work out what the special organisation of the critical state is that applies to all these things, if after they've run it through again and again, they can't tell when an avalanche is going to occur. You say you can't tell when this big forest fire is going to occur, and so on and so forth, although there is a critical state condition around it. So I haven't quite got it.
Right. There is a very definite pattern that emerges in the system, and which is the signature of the critical state. However, it doesn't emerge at the level of individual events. So you cannot predict what the next grain of sand is going to trigger, whether it's a small avalanche or an intermediate size or a large avalanche. However, you can predict that if you do drop 1 million grains and count up how many large avalanches, how many intermediate avalanches, how many small ones there are, and make a plot of those statistics, there's a very definite pattern that emerges at the level of the many events and the statistics of those events.
How does that work with world wars, financial organisations and forest fires? How does that same system pull over to that? Because the real experiment you've got is looking for earthquakes, and that doesn't come off in your book.
Well, it does.
It doesn't. The guys who turned up, like waiting for the sort of second coming for the earthquake, with the best instruments in the world, you say, never have so many instruments and so many geophysicists been in one spot at the same time. They worked out the earthquake was going to happen. It was 12 years ago. It still hasn't turned up.
Mark would say,
I'd say exactly. I agree with that completely. The trouble is that an earthquake, it appears now from the mathematics, is an event of the very same kind as one of these large avalanches triggered by a single grain.
There's two different things here which I think have got a bit confused up. There's power laws and there's critical states, and these are quite different in my mind. Power laws are much simpler to understand. If you throw a potato against a wall and it breaks into lots of bits, and there'll be a lot of small pieces, there'll be a very few large pieces. And what the power laws show you is that if I compare those of 1 millimetre size with those of 2 millimetre size, there'll be half as many of the latter. If I then compare the 2 millimetres with the 4, there'll be half as many of the 4 millimetres, and so on and so forth. And it doesn't matter how big you are, when you compare this big with twice as big, you get the same ratio each time. That's the sort of power law. Now, when does this happen and when doesn't it happen? It happens when you're far away from anything that's, quote, important in the problem. For example, the potato, there's 2 critical sizes. There's the size of the potato. You obviously can't get a bigger bit than that. At the other extreme, you've got the very small molecules that make up the potato. You can't get smaller than that. As long as we're talking about bits of potato that are much bigger than molecules and much smaller than potatoes, these power laws happen. When things get interesting is when you get to the size of the molecules, and then you start getting very detailed things that happen which are inherently unpredictable, and that is when critical phenomena that Mark is referring to, I think, really come into their own. Earthquakes, the rule there is that you can't predict when an earthquake will happen, but you know that there'll be more earthquakes of size 5 on the Richter scale than of size 6, and in turn of size 7. They get rarer and rarer as you go bigger and bigger, but there's no inherent...
What he's talking about is Zipf's law. Now, what you can see is that if something is considered scientific now, it's scientific because it makes predictions. But that doesn't allow for any access to the laws of chaos, which we know by experiment are true. But the laws of chaos have proved scientifically that some events in the universe are completely unique and unpredictable. That's what you need to be able to say. And you can do, that is a scientific statement to say, we've proved scientifically that these events in the chaotic pendulum are not predictable. They're completely, infinitely unpredictable. Now that's science, but you haven't recognized it because you're trying to say it's only science if it's predictable.
Right, okay.
But a chaotic pendulum is a scientific experiment which shows that some systems are unpredictable.
Unpredictable.
So you're missing the science, and they haven't explained it very well, especially when they're talking about potatoes being thrown against the wall. It's all a bit confusing.
Limit the size of earthquakes. They just become rarer and rarer.
But isn't the basis of science predictability?
So it's just said,
yes.
So it's just said, isn't the basis of science predictability? Well, chaos theory is excellent science, and it's based on unpredictability.
Right, okay. So
So
yeah, even the presenter is stuck in the old paradigm of classical physics.
Yes. So it's saying if it's not predictable, therefore it's not science.
It can't be science.
It can't be science, even though we know that chaos theory is as experimentally provable as classical physics. So that's the problem. You've got the wrong misconception that you're trying to apply to nature.
Right, okay. And what can be proved with chaotic physics is that science is unpredictable too.
Yes.
And that's scientific.
That's scientific. So
right.
Poincaré has written a mathematical proof stating there are no solutions to the three-body problem in space. No solutions. And that is good science. Mathematical proofs are absolute, so we have to stick with them.
Right, okay. It's a lot. Yeah, I'm really glad I've gone through this week because it's a lot clearer to me. So science is both predictable and unpredictable.
Yes.
Right.
Yep. So again, it's the same old problem.
Yes.
Is it quantum mechanics or relativity? No, it's both.
Right.
Is it chaos or classical physics? No, it's both. Is it male or female? No, it's both.
Right.
So it's, again, the human failing, trying to stuff nature into the wrong misconception. So it was Newton who came up against the three-body problem. As long as the three bodies are equal size, that's what they all miss. If you've got a very large body like the sun and the planets, it doesn't work. Or a gas giant and its little moons, doesn't work. I get a completely different kind of system. I get a regular system, which removes differences between the bodies and brings it into a state of self-organization.
Right, okay.
So that's a very, very important thing which is just missing. So let's get back to the program and see how they get on.
And no, it depends what you mean by predictability.
Well, if you do the same experiment again, you get the same result. That's what I mean by predictability.
Oh, in that case, yes.
So there, if you do the same experiment again, you get the same result. Now, in the case of a chaotic pendulum, the same result is that you can't predict what it's going to do. That's the same result. No matter how many times you do the experiment, you always get a different answer. So you've proved that your science is good. There are now answers to the three-body problem.
Ah, yes.
So that's what's missing. Clear
explanation. And it's okay. Yeah, and it's okay not to know, isn't it? I think
yes. It's absolutely what the universe needs to become more diverse and complex.
Yeah, exactly.
It's not all pre-stated.
No, and I can understand why a lot of science is in that old thinking, because there's a kind of comfort, isn't it?
Yes.
There's comfort in isn't there?
Yeah.
Like, we need to know the answers. We need to know if this happens, we need to know what and why it's out.
Yes. So that is gone. So if you consider a human being, it depends on what environment you put that human being into, what it becomes.
Yes.
And that is infinitely variable, because every human being will have a different sequence of events which become your life. And it's not all preset. It's not preset like physics. The shell lands in one place every time. Whichever environment you put the human being in controls the behavior of the system. So it's just the same old problem. So let's get back to see how they get on.
I think the experiment here is that if you wait 50 years, I can predict that, say, half of us will be dead. And if we wait another 50 years, another half of people then will be dead. But when exactly we will die in that period is inherently unpredictable. Now, I regard that as science on a statistical sense, not on a day-to-day sense.
Right. I want to bring it back to the title of your book. You call it ubiquity, and we all know what that means. And you write, at the heart of our story lies the discovery that networks of things of all kinds, I'm quoting, atoms, molecules, species, people, and even ideas have a marked tendency to organise along similar lines. Now, that's a big claim, and it's back to the idea that everything is water of Thales and onto the theory of everything which is being worked out. Can you just say briefly what in your book would persuade us that that was the case?
Well, there's two levels, I think, of persuasion. The first level is that this mathematical form for the statistics of events, large events, intermediate events, small events, that conform to this pattern that Frank described called a power law. It shows up in earthquakes, it shows up in forest fires, it shows up in the fluctuations of financial markets. If you look at how much prices change over, say, a day, over a week, it shows up in the statistics of the number of citations that scientific research papers receive. You find very few papers that receive a huge number of citations, very many that receive a few citations, and nevertheless, over the whole range, there's a terrifically simple mathematical form, which is the power law. And physicists only know of a few mechanisms that can give rise to power laws, and one of these is this notion of the critical state. And it seems to be the most widespread possible explanation for this particular kind of pattern. There's a deeper answer, and unfortunately it's a bit technical, but it goes into a concept which is known as universality, and it's called critical state universality. The critical state was discovered originally not in the context of a sand pile, but in the context of what physicists call a phase transition. This is when a liquid turns to a vapor, or a magnet, if you heat it in a furnace, eventually becomes not a magnet. It loses its magnetic power. This is called changes from one phase of organization to another phase of organization. This is widespread in nature. Many materials do it. And if you poise a material right on the boundary between two phases, then you find this critical state organization. And it turns out that extremely different substances that have no similarities in their molecular workings show exactly the same critical state behavior, even down to the numbers, several significant figures describing the exact precise patterns that you achieve at this critical state. And there's a deep theoretical reason why it turns out that the details don't matter. So it's very plausible that one can find the same kind of organization welling up in systems such as the level of earthquakes or forest fires.
Frank, can you comment on that in terms of theories of everything and the present state?
So what he's talking about there is the self-organization of systems.
Yeah.
Now, self-organization cannot come from any law of physics which only seeks uniformity and equilibrium. That needs to be stated loud and clear. On top of physics, if you have other kinds of systems which have self-organized criticality, which we know things like the solar system does, they continually reorganize themselves, even if you mess them up. And that can't be explained by any law of physics, so it's a complete mystery as to how the self-organization of something like a snowflake or a solar system take place in terms of physics. So once again, just having the laws of physics, the second law of thermodynamics, which only seeks equilibrium, you can't explain nature. You need layers and layers and layers of other mathematical rules which do explain exactly what we observe.
Of a theory which explains everything. First of all, do you think that theory is lurking around at the moment?
You keep hearing this, and I'm actually very sceptical, that when you look back in history, people have at various epochs thought that they have got a theory of everything, and what they really meant was we've got a theory of everything that we are currently aware of. I think that nature has a very sobering effect on us, which is it reminds us that we are not as clever as we think. That in the last century they thought that they had got an understanding of everything that was then known, mechanics, electromagnetism and so forth. There was a little problem on the background which was called the black body radiation problem, and that led to quantum theory, which completely revolutionised science and developed the 20th century electronics industry and technology, among other things. In the 1930s, at last one had, if you like, the equation of everything on a T-shirt. We now call it the Dirac equation, which describes the way that electrons behave in atoms. That equation, in principle, underpins everything in chemistry, biology, life.
So that, the equation, the Dirac equation, being able to explain how molecules work doesn't explain how DNA works, or biology, or a human being. So it's got to be like that, because how the molecule works allows the next step to take place, but then you need another set of rules on top of the previous set. So that's what he's not explaining well. The physics allows everything else to take place. So it's like having a stage on which chemistry and biology can play out. The stage allows it to play out. But the self-organization of the play is very different from the uniformity of the stage. So that's how it works. Physics allows everything else to play out. The layers and layers of mathematical rules on top of that physics are much, much more complex than just the physics. If you're trying to explain play just by looking at the stage, you'll never do it.
Nobody's solved it.
What about now?
At the moment, we are again at one of these states where all the phenomena that we have seen and know, we are getting very exciting feelings that there is a unity to them, that we are analogous, if you like, to the 1930s, of being able to write an equation, not quite on a T-shirt, let alone to be able to solve it, which in principle might describe everything that there is. Whether it does or not is for experiment to decide, and I think, exciting though this is, ubiquitous as it is indeed the experiments that will be performed in about 5 years from now at CERN that are going to go to extremes, the first moments after the Big Bang, if you like, simulated in the lab, to see if it really was like that, or whether we only just think it was like that. Because if it turns out that those experiments show there's something out there that we haven't dreamt of yet, we will have to take that on board and revise everything.
Nancy Cartwright, do you think that this search for a theory of everything, a solution or a cluster of facts in ubiquity which make for a solution, do you think that that is some kind of religious impulse as much as anything else?
I think that Frank thinks that, and I'm not very clear about the psychological motivations that drive us. I know that it's something that has come again and again throughout the history of humanity. We look for unity. We never achieve it. But I don't think it's the only metaphysical or religious drive we have. I think that there is the exactly counter drive that well, there's the simple way that people think in terms of intellectual history. It's between the Enlightenment and Romanticism. And in a sense, the Enlightenment stood for unity, unity of all people are the same. And Romanticism has been a movement that says, pay attention to the differences, pay attention to nature, which is highly varied. And I think we have both drives. I'm very fond of, the reason I call my book The Dappled World is because I'm often confronted with this aesthetic or religious ideal of unity and told that if one gives that up, one's giving up the whole beauty and excitement of physics. And I myself have always had a totally different aesthetic. The one of Gerard Manley Hopkins, who says, his poem Pied Beauty, glory be to God for dappled things.
Yeah. I want to come back to this idea of ubiquity to end on there. Mark Buchanan, you do suggest in your book that human history, that human history may be governed by the same underlying principles as govern the fluctuations in this pile of sand. Let's go back to this intriguing pile of sand. Could you briefly tell us how you make that leap?
Okay. Well, again, it's through this mathematical pattern, which is the power law, which is a very special kind of pattern that you don't find arising very easily in nature, at least on our earlier understanding. And now it seems to be emerging in many different cases at many levels. It turns out that there is some statistics on. It's not easy to get a mathematical handle on history, of course, but if you try to do so, you can look at, for example, the statistics of the wars that have occurred over the past 5 centuries. And there's a guy from the University of Kentucky named Jack Levy who's done this, and he finds a quite accurate power law for if you take the grimmest of all statistics, which is the number of casualties, just to get some measure on the size of a conflict. Then if you look over 5 centuries, wars follow exactly the same statistical pattern as do earthquakes. So even though it may shock our sensibilities to believe that the political fabric could somehow be following a pattern that is quite similar to the way stresses and strains build up in the Earth's crust. Perhaps they also build up in the fabric of international relations. Certainly the mathematics suggest that is a possibility. And all I really want to suggest is that one ought to take on board the idea that is a theoretical possibility, and instead of trying to interpret these complex systems in terms of older ideas from physics, be they cycles or simple linear progressions, we ought to start to think about the kinds of mathematical patterns of change that arise in the more complicated systems that physicists are now looking at, such as the pile of grains.
Well, thank you all very much indeed. It was, I hope people were as enlightened as I think I am a little bit. Thank you very much. Next week I'll be discussing the Tudors.
So there we are at the end, he does nail it and says that we've got to stop thinking like we have done in the past. And once again, it's the failure to see the laws of chaos as a new set of laws which govern physical systems, and the failure to see that mathematics provides governance of all physical systems. It's those two failures which are holding back the whole of scientific thinking. And that was a very, very muddled program, which can all be explained if you've got the right examples. So a very, very interesting program that
for sure.
Just all needs to be brought together, which is what you and I are now doing.